Welcome to the SNIA Experts on Data podcast. Each episode highlights key technologies related to data.
All right, welcome everybody. My name is Eric Wright. I'm the host here of the SNIA Experts on Data podcast and the Chief Content Officer at GTM Delta. And I'm extremely proud to be able to have two amazing guests with us today. We're talking DNA storage. We're really going to dig into all of the work that's going on inside and outside SNIA related to the DNA Storage Alliance and a lot of the work around there. With that, let's just jump right into the people that do matter on this podcast. We have Esther and Dave, and I'll ask you to just quickly introduce yourselves, and then we're going to talk about the efforts that you've done. What is DNA storage for folks that are new to the idea? And we'll just keep on diving in. The only thing I already know, I want longer than we've got to talk about this because this is such a fantastic and fascinating topic, and the potential opportunities is amazing. In my view, and I'm sure I'm not the only one that shares that. So with that, Esther, do you want to introduce yourself?
Yes, thank you so much for having me, Eric. My name is Esther Singer. I work at Twist Bioscience, and I'm Director for Product and Market Development for our DNA Data Storage business unit. Thanks for having me.
And Dave?
Yes, and likewise, thanks I'm very happy to be part of this, Eric, and nice to meet you. My name is Dave Landsman. I'm a distinguished engineer at Western Digital Corp, and I'm part of the research and CTO team, and I work on standards, and I also have become, I'm a SNIA board member and also a co-chair of the DNA Storage Alliance, which we'll talk about today, along with my other co-chair, Esther. Yeah.
And the good news too is for folks that are watching this on YouTube, you get to see your beautiful smiles, along with we've got links in the show notes down below for some of the announcements and some of the initial spec papers. So definitely worth a read for people that want to dive in. But I think let's give the elevator pitch. What exactly is DNA data storage? Because this is probably a fresh concept to a lot of people on what it is that we're trying to achieve here.
Okay, so let me jump in there. I think we want to. I really think that's a few questions mapped into one, Eric. And so first, let's talk a little bit about the why DNA storage. Why are people considering it? And there's a couple of main aspects to that. In the broadest sense, why are people even thinking about DNA data storage? And the answer is that people are considering, we're storing everything digitally today, in all fields: healthcare, astronomy, climate science, national libraries. And so there's this explosion of digital data that people are wanting to save. And we talk about getting into the so-called zettabyte era. A zettabyte is a billion terabytes. So we're seeing this exponential explosion of data being saved, and this is causing some issues. It's increasingly expensive and impractical to save all the data with the existing storage technology that we have: SSDs, HDDs, tape. So the expenses in energy and technology refresh, having to refresh the actual media and stuff every 5 to 7 years, the sheer size of the data centers. So as we start scaling on, orders of 1,000x over the next 10 years, the expense of saving it in a traditional or existing storage technology is causing a dilemma. I call this the save discard dilemma. I may be throwing away value or knowledge or even future discoveries if I throw the data away, but yet I can't afford to keep it on existing storage tech. And the trends in artificial intelligence and machine learning are making this dilemma even more acute, because we have more and more effective ways to search and full value out of this data. So we don't want to throw it away. So in this context, people are looking at new storage technologies like DNA, like glass, like new ceramic materials, etc. So why DNA specifically? Because that's what we're here to talk about. And I'll let.
And I can talk a little bit about what's cool about DNA. So there are a number of features that make DNA extremely attractive for data storage. One thing is it's very long lived. There is actually no long-term digital data storage medium today. Hard drives, disks, tape, they all have to be replaced within 3 to 5 years because they fail. So if you want to keep your data safe, you have to copy it onto a new storage device. DNA can last for thousands of years. And in fact, the oldest DNA that we've retrieved was from a relative of the mammoth, 2 million years old, perfectly intact. So DNA can be stored in a way that can last thousands of years and keep your data safe. It's also extremely dense. And the density comes into play when we're thinking about the vast amount of space that data centers are taking up today and all the energy that goes into maintaining these data centers. You can store hundreds of petabytes of data in a gram of DNA. I mean, think about that. So a petabyte is 1,000 terabytes, right? And on one of these cartridges, tape cartridges, you have about 18 terabytes, maybe 40 or so. So that's thousands of these tapes in a gram of DNA. That's the theoretical power in terms of storage density. DNA doesn't require any power to store. So once it is in its form, it doesn't need to be on an energy grid. And in this day of age where energy is becoming more expensive and we need so much more of it, this becomes a very sustainable solution. And then there's a few things that are just game changing, that are not really easily compared to what we see in the storage world today. So one thing is you can make 1,000 copies from a single original in an hour for $1. So every time today, if you want to make a backup, that's 100% of the cost. And what's stopping most people from making more backups in case of a disaster is cost. And then there's other game-changing features such as the portability of DNA. Because it is so small, dense, and lightweight, you can really transport data. You can distribute data geographically. And then, DNA, as opposed to many of the other technologies, is something that will just not go out of style. And I think that's what most customers are looking for. They're not looking for the next Blu-ray. They're looking for something that will persist. And as long as there are humans around, DNA will always be interesting to use for research. So the tools that we use to write DNA and to read DNA will always be around. So all of these features that make up DNA, all of these benefits, we think make it an excellent data storage medium. It already is, and it'll only become more and more dominant. And it'll also lead to lower total cost of ownership in the long run.
It's amazing when I think of, of course, the first thing we think of is like, this is the beginning or maybe even the end of so many science fiction movies that we've seen. The idea that like they've encoded something in DNA, and like I said, we could find it 1,000 years later, maybe in a little piece of amber. Then we build an island and we restart dinosaurs. Let's maybe avoid that one, but like, hey, they can restart my Ruby on Rails app in 2,000 years off of a mosquito in amber. But at the real level, there is incredible possibilities that are active today. Yeah, Dave, sorry.
If I could make one comment on that point, I mean, it is, I've got all kinds of funny questions when I started getting into this field. Like, people said, well, does this mean I'm using DNA for storage? Am I putting storing my music in my dog, right? And things like this. And when it is important to say, I think, that the synthetic DNA that we're using for storing digital bits in DNA is synthetic, And there's really no, I mean, there's minimal to no risk of creating life, and we're certainly not using, biological
Right.
organisms. We're using the building blocks of the molecules to store data. So I think it's important to say that. And
Yeah, when it's because this is even when we talk about things of like occurrences of patterns in life, and I had one presentation I did which it opened with just basically like a honeycomb and like a sunflower and stuff that observes. We basically have made a science out of observing patterns that exist. And then you get this funny thing at some point where people go, "Oh, that's interesting. So bees know math." And you're like, "Oh, no, it's actually the other way around, that bees create a thing that we observe, and we have mathematical representations of what they do. It happens to be perfectly mathematical in its symmetry, etc. But we are observing the pattern and then replicating that using other tools and techniques." So kind of to what you said there is that we are learning from the biocore of the origination of it, and then we're able to replicate that synthetically, which is really an incredible thing, thanks to just so many innovations that have got us up to this point in time. But I think the most important thing that I want to, well, not the most, an important thing I want to talk about is how do we do this as a group, as a collective? Because the DNA Storage Alliance is interesting in how that came together, and then the relationship to how you started to pair up with SNIA. So I'd love to hear both of your thoughts on what is the DNA Storage Alliance and the purpose and what you like about being able to work in a large group that has diverse views, lots of people that are innovating together, even though we potentially even work for competitors in the industry sometimes. It's such a neat thing in how standards organizations can work together.
so, um, so I'll start with that one. So the DNA Storage Alliance, which now constitutes about 40 member organizations, it was formed in 2020 as a group of small companies, a group of companies and universities. Sorry, not a small company, a group of very, from major to startups and universities. And we had a goal of wanting to create an interoperable DNA data storage ecosystem. So the way we were independent of SNIA, and we were debating whether to, do we incorporate ourselves, or how do we grow? And because we wanted to start not just talking together, but to actually potentially write storage or write specifications and standards. So as far as our journey with SNIA, we joined in SNIA in 2022. And we felt that we looked around at options, and we felt that SNIA's expertise in standards development, as well as its established breadth as an industry association, would help us drive. It would be a good platform for us to drive the mission. And as far as standards, standard setting, it's kind of an interesting thing to try and create standards are in such a nascent ecosystem, right? People think usually when you create standards, it's in a field where there's a lot of technology. It's many people are solving a problem in different ways, and we're trying to unify in some ways so that we can be more efficient in the ecosystem and grow things. This is the essence of standards. So we are trying to be and yet we felt that certain specifications and things could help bootstrap this nascent ecosystem. So we wanted to do that we wanted to create some specs and standard ways of doing things without stifling innovation. So the Alliance has created a few standards. One is called the Rosetta Stone. It's kind of a master boot record, if you will, for how you dig into a DNA archive and identify how it was built and how it's structured. We have a standard called the DNA stability evaluation method, which is about evaluating the capabilities of DNA containment systems to store the data. Because, as we were talking before, we've recovered data, DNA in fossils, right? That is millions of years old. But when we do it when we do commercial storage of DNA, we're going to build containment systems, and those containment systems will have different capabilities and costs and flexibility. So we felt this evaluation method here would help do apples to apples comparison of preservation methods. And we're also working on interoperable interfaces, which is how, if you put a DNA storage system in a data center, how do the pieces interact, and what kinds of interfaces need to be standardized so that we can have different vendors contributing solutions. So that I've rambled on a bit, but that's kind of the SNIA, the DNA Storage Alliance, and SNIA story.
Yeah, and I would add, Eric, that when you are building such a groundbreaking new technology that is trying to disrupt an existing industry, it takes not only a village, it takes the world.
A multitude of villages with a common goal.
Yes, right, because there are vendors, this is a semiconductor-based technology, there are fabs, there are strategic partnerships to be made and utilized. There's the voice of customer. There are so many players in the field as it exists today that all have to come together as well in order to help this technology get to market. And so the alliance is absolutely critical for DNA data storage to become commercialized.
And I'm going to ask a question of you, Esther, given that you're coming from, I'll say, the other side of it. So coming from the biosciences world, and then where you've generally leveraged technology, not necessarily thinking that you would be defining technology. How does this, how did this come into your world, and what does it feel like relative to some of the other, projects you worked on leading up to this work?
So this is super exciting because we are working at so many different interfaces. And every time I feel like you work in an interface of something, that's where you have a huge potential for real revolutionary new tech and, real problems real solutions to existing problems. And so in this case, we're bringing together the semiconductor world and the synthetic biology world, right, in a completely new way. And like I said, the data storage industry has been around for a long time, but it hasn't really been disrupted in a very long time. And to learn about this new world, the data storage world, to me new, to everyone else like Dave existing for a long time, and learn about their pain points and how the biology world can actually help address these pain points it's like a match made in heaven, right? And so it's this constant interchange, this exchange of how can we help each other to not only bring a cool technology to market, but to actually help humanity and store data and preserve our legacy. So it has a bigger purpose, and it has there's a drive to do this, and many people believe in it. Many people see that it's not only cool, but there is a big market as well, right?
Right.
And it can really, be here to stay, and it will be.
And there is a beauty to the unlikely friendships that likely have developed because of the ability to cross over. And what we often find is that, like, I've been in technology for a long time. I'm a nerd at heart, but I've always thought about why it matters. I say, what do I do for a job? I give emotion to technical content, right? I turn speeds and feeds into business needs, understanding the technology, but relating it to what it can actually do and how it can create benefit for people. And this is the beauty of solving a very complex scientific and semiconductor, like these are physics problems that we're solving. But as a result of doing that, the breadth of capabilities we're now going to open up to the rest of the world as consumers for this is incredible. And doing so with that standards-based approach, like you mentioned, Dave, it's like it's sort of a slow down to speed up. Let's make sure that we're all building from the right base. And in doing so, then that actually speeds innovation, which is counter to what people think. It's like they often think of regulation as slowing innovation, but in these cases, it's actually quite the opposite. That now, if we know here's our specification that we work from, then when we get into like interchange and interoperability, there's no question that whatever you build, if it's built from spec, like it's immediately you can play with this ecosystem, and that is a boon that I think we've learned, sort of from open source of like, we don't have to be from the same, at email.com company name in order to contribute to this, but everybody can benefit from us all collaborating together. So it's pretty amazing to see.
Yeah. And, to elaborate a little bit on that point, I think it's super important that, what we're trying to do when we set any specs or standards here is to draw some guidelines and boundaries around where pieces of the DNA storage pipeline need to interact, but to allow innovation around those boundaries, which is the essence of what people try and do with standards in general. It's just particularly challenging when the core technology is quite nascent. But we do feel that we can promote the growth of the ecosystem by selectively defining some specs. And we'll leave things like, we're not going to try and define like, how does the chemistry of tagging objects in DNA. There's many ways to do that, right? And we don't want to, and those are very vibrant areas of research and development. So we don't want to specify those, but we can specify, how you characterize the capabilities of a system or other aspects that don't, that don't get into the implementation, but help the ecosystem come together. So,
and it is truly a bi-directional win in my view of like and Esther, you're probably seeing this, is that you may be making discoveries on other ways to leverage DNA as a result of us trying to build an application towards this, because we may find that nature has found a way to do a lot of the things that we're trying to do in a synthetic. And as a result of that, we may actually do more discovery through synthetic to organic applications. It's such a beautiful world for us now to be able to have more reasons to get down to this level of discovery and then build back up from it.
No, absolutely. For the longest time, what's been holding DNA data storage back to actually becoming a product and to become competitive cost-wise compared to all the other existing, drives and tapes, is the cost of DNA synthesis. So DNA synthesis, is something that Twist has already scaled and therefore, taken the price down. And for DNA data storage, you have to do the same thing, but several orders of magnitude further. And so that's what we're working on. And you can extrapolate from there. If we can make DNA even cheaper to synthesize, you can make a gene even cheaper to synthesize, an oligo fragment. Lots of different DNA-based products that could go into other applications of the synthetic biology. For example, for oncology research or agricultural research, materials and sciences. There are many applications that use synthetic DNA besides data storage, of course. And so all of these, fields of science and tech can benefit from the advances that are coming out of driving the DNA synthesis technology further to become competitive in the data storage world. So you're spot on there.
Well, and it's the interesting thing is we get to teach each other in ways that now we're basically creating a language map between storage and synthetic, biorepresentation. It's also probably fun that you get more people get to say deoxyribonucleic acid. How often you get to say that in a storage community? It's actually kind of cool. But on the other side too, Dave, did you imagine at the start of your career and moving into Octo and some of the R&D that this would be an area that you'd get to explore in your career, let alone lifetime?
Well, that is a great comment because no, the short answer is no. And, I've been in, I've got a computer science, electrical engineering background, and I've been in the tech industry for, decades. But this area of, mapping the wet lab chemistry to the chip and actually creating using molecules to store data and potentially even do compute operations in the storage is just mind-boggling, and when I first kind of encountered it, I frankly thought, boy, is this really science fiction? And the it was clear to me after I got into it that it's not science fiction, and it's we're starting to see the blending of these the chemistry and biology with the semiconductor technology to be able to actually do things with DNA as a medium. So it's been a complete joy for me, I have to say, to get involved in this, and I'm very excited about it.
And I also think it's a counter to everybody that, and I work and I've got a lot of friends in the storage industry. I've got clients in the storage industry, and I've been a fan I've run data centers at scale at big companies, and I've worked with a lot of storage. And the thing that I always find consistent is that we always say, I know we're just a boring storage company. Like, don't say that. It's fantastic what you guys do. I like that storage itself is boring, that it just works. And I like that it just works. That part should be boring. I want it to just work. I don't want to I want it to be less exciting and, in alerts, but I sure love, even just today, moving from spinning, platters to the point where we have long-term successful storage. It's, on persistent memory, just even to explain the idea of NVRAM concepts years ago to people of, they're like, wait a second, do we actually trust this to hold data for a period of time? And I got told we couldn't keep stuff on CDs because they'll physically degrade. So put it onto USB sticks. And then somebody said, well, wait a second, those aren't going to last forever. And we'd been injected with this idea that it naturally must have a failure rate and a degradation just like it. And then we go to this next level where we're looking at, biorepresentation in synthetic that we carry over to storage. And no one can say well, I don't know if this DNA thing is going to stick. Well, I don't know. It's been around for a couple of years.
Yeah. Maybe this is a good point to explain to the listeners how DNA data storage actually works. We talk about it as a concept, but I think it's important to just see that it's nothing scary. It's like David said, we're not storing data in animals or humans. So what DNA data storage really entails is the write part, writing DNA, storing DNA, and reading DNA. And for example, this podcast could be stored in DNA. What this podcast is made of is zeros and ones in the digital realm. And what you need to convert these zeros and ones into the DNA code of ACGT is what we call a codec. So this codec translates between these two languages. It also has other features such as an error correction algorithm built in. It makes sure you store your data efficiently in DNA. And so you start with your podcast in zeros and ones, and you turn that into the components of DNA in ACGT. And then you write DNA, you synthesize DNA. So, and that's done using a DNA synthesizing machine. And then you come out with these molecules, these physical molecules of DNA. If you were to look at them, it would just be a transparent liquid. You wouldn't really see very much, right? And this DNA, all it encodes for, again, is your podcast. There are no genes, there's no biological function. And there are rules, right, for what we can actually write in DNA that we have to adhere to. So now you have your podcast in this DNA molecule, in this transparent liquid. Now you need to store it, and we can store it away from the three things that degrade DNA. That's UV light, oxygen, and high temperatures. As long as you keep it away from those three things, your DNA is safe, and your data, your podcast, will be safe for thousands of years. And people can then read it back in 1,000 years and see what we thought of, when DNA data storage was still nascent. Whereas in 1,000 years, it was probably going to be in everybody's computer. And they can read it back with a technology called DNA sequencing. It's again a machine that takes the liquid out of your storage container. I actually have one of these storage containers on my desk. This could be one of these, right? This is a stainless steel capsule. This capsule could have several terabytes of data inside. Compare this with a tape of this size, which doesn't have that much more data. It's also, tens of terabytes. So you can see the volume and density difference. And so you read your data back, and you get out ACGTs, and then you apply the same codec that you used to translate the zeros and ones into ACGT to translate it back to your digital file. And out comes your podcast that you can watch on your computer. So that's really the workflow.
Yeah, and the good thing too is the links in the paper to the specs. We talk about the concept of sector 0, sector 1, the ability to do mapping and understanding, and effectively, when I look at it from that layer, like, oh, it's just another object store. It has attributes, it has parameters, it has capabilities that we expose through those ways, and so the artifact is easy to map onto it. And then now on the hardware side, then Dave, you and the rest of the hardware world gets to build those, sequencers and how do we get it in, get it out? And then what are the actual practical use cases we have right now that you're sort of looking at? That would be probably the first thing to look at, because it's the other thing with being nascent is we think there's 1,000 different things we could think of. But then when you ask somebody for a specific, it's very hard to come up with a singular one. So I'd love to hear, do you have specific practical applications that you're aiming for or achieving at this point?
Yeah, I think because of the nature of DNA, meaning its longevity, its density, and its portability, the use case of archival data comes to mind immediately, right? I think up to 80% of all data in the world can be considered as archival. So very little data is actually accessed frequently and is computed on. And most of it, if you think about your own data files at home, your photo albums, how often do you actually access a picture or a video that's older than 6 months? At the organizational level, it's the same thing, but nobody wants to throw any data away. And so that data needs to be stored somewhere. And the best way to store it, not only the safest way, but also a way that leads to lower total cost of ownership, the most energetically friendly or environmentally friendly way, is on DNA. So that's long-term archival. There's also this use case of backup and disaster recovery, right? So that goes a step beyond. Once you do run into a scenario just like Universal Studios, 2008, where a big fraction of their library burned down, their archive burned down, right, and hundreds or tens of thousands of original artworks forever.
Not replicated anywhere. And that was, I remember even hearing we've lost the first 10 years of the Tonight Show of, that's one I recall, but there's so much that's just gone. because there was no second place to keep it.
Correct. Yes. So having a backup, sort of a gold standard on DNA. And again, you could make 1,000 copies in an hour for $1 of the same artwork, could just prevent that same situation from happening again, where you lose something forever. And then, again, because it's portable and relatively lightweight, you could distribute your data a lot more than you have today. Today, we're really thinking about data centers when we think about data storage, right? Everybody's uploading stuff into the cloud. And the cloud is not a nebulous thing. That's data centers, right? That's drives and tape, physical objects that are storing your data. But data centers aren't existent everywhere in the world. There are hubs for that. With DNA, you could sort of distribute your data a little bit more geographically, and have it where you actually need it. So it's sort of democratizing. Maybe, I don't know if that's the right word, right? But you could think about having an efficient data storage that is no longer tied to the quite extensive infrastructure of a data center as we have it today.
And definitely when we think of the amount of data being created on a daily basis, I think, sort of YouTube calls out this, that there in the next 24 hours, there will be more YouTube videos uploaded than there were in the first 10 years of YouTube. That's today. That's not slowing down. Right? And that's one example of thousands of applications. And then we get commercial applications. We see a lot of the hyperscalers, they're offering the idea of like sending a data store to you load your stuff on it because of bandwidth and throughput capabilities, because we can't do it over the wire, nor can the network, not only can the network not handle it, but it's expensive to do it that way. And then from there, so like there's all this expense and toil to get to the final result, which is kind of then expensive long-term storage. So it is such a fantastic thing at every layer. And Dave, on your side of it, of course, being the one that has to deal with that interchange and moving data in and out of these things, because data is used for other things. It's not just data by itself. It's data that drives applications, and that we build whole ecosystems on top of. Where are you seeing the practical applications on the storage side with where you're working?
Yeah, so I think there's no doubt that the initial use cases of something like DNA storage will be for probably deep archival use. But like we've discussed a little bit throughout the time here, what you're essentially doing with DNA is you can think of retrieving the whole archive, or you could think of doing a key value access or an object access for something that is stored. And of course, at the molecular level, we have to add the object tags and things like that so that we can do it. But at the storage stack level, it's pretty much a standard access method. With different performance and latency characteristics, etc. But today we have a basis for a read store, a write store read pipeline for archival, but we're working on, and not like the entire DNA ecosystem is working on enabling low-level operations for random access and object access. So this will, and this involves what I refer to as, chemical instructions. So using the molecular power of DNA to and the complementarity within the molecule, so that you can have probes that go in and pull out an object versus pulling out the whole archive. So these are things that people are working on, not only for storage operations like read, write, delete object, not just the whole archive. People are also looking at index search and ways to potentially search the archive, because of course we don't want to throw this data away, and DNA enables a cost-effective way to store all the data without and not lose it. But then we have to find what we're looking for. So these random access methods that are being looked at and are super important to move DNA beyond kind of the all archive, deep archive use case into more active recovery and search. If I made sense there.
Yeah, no, and I think that what that lights up in my mind is that in the same way that we often say, we want to go back to the moon, and people say, why? Like, we're not going to move to the moon. We're not going to develop societies on the moon. But what they don't necessarily understand is the amount of innovation that occurred as a result of things we did in trying to get to the moon. And to the point where we call these moonshots now, right? But this is a moonshot that, number one, is actively delivering use case capabilities on both sides, on the bio side and on the metal side. And as a result of work that we're going to do for each of us to solve each other's problems, are likely going to open up use cases in both camps. And we will quietly discover incredible innovations and optimizations we can likely do in the way we store, retrieve, and manage storage today. Like, even looking in databases, it was one I noticed recently. So sorry, I'm going to go into specifics. I used to use a MySQL, and I moved to Postgres because it's supposed to be more performant, and it just took my brain too long to convert to Postgres. But I use Ruby on Rails all the time, and it ships with SQLite. And I get told all the time, like, don't ever use it in production. It won't scale beyond X. But what we did in trying to make all these other platforms work was we've discovered innovations that allowed, in this case now, SQLite, as an example, now operates incredibly well because of things we learned through trying to solve storage problems and retrieval problems and query interface problems that got rolled into this tiny little thing that is now fantastical to where it was 10 years ago. And I think this is not necessarily that we're going to say in our lifetime the world will move to DNA storage as primary storage. It's the fact that in our lifetime, at least of the three folks on this call and folks that are listening, we're going to see innovations that you won't realize are tied to what's going on right now in these alliances and in these standards bodies and in the experimentation you're doing. So first of all, bravo, and thank you for doing things that you may not see yourself get an award for in your career, but knowing it's more important for us to move towards an answer than to, we have to make moves that could take a long time, but that's the only way we get there.
But I do think it's important to say, I think we'll see archival use cases come to fruition, and in much, in the next 5 years or so, right? It's just my personal view of things, kind of hovering at the Alliance. Whether we'll get to more, whether and when we'll get to more flexible use cases, I think that'll take a bit longer, but the technology is moving, thanks to companies like Twist and many other Alliance members who are working on solutions.
It's definitely, I get excited when I saw the chance for us to speak on this. I just thought, wow, like, when could a lowly shoe repairman when I was in my teens who would make his way into technology, that now I would be speaking to two folks who are part of something that's leading us in a fantastic direction as a storage and a bioscience world. So this is awesome. So thank you very much, both of you. And on the way out here, I'd love to ask Esther and Dave, anything you would suggest for folks to maybe go take a look. We'll have links, of course, to some of the spec that we shared in the press release about the DNA Storage Alliance. But where are good places for folks to maybe reach you, as well as to look up more about the work that you and the teams are doing?
Yeah, would love to hear from folks who are interested to know more about DNA data storage. We have an email address, info@dnastoragealliance.org. I think we'll post that here. We have a LinkedIn channel at DNA Data Storage Alliance. We have a Twitter channel, and we also send out newsletters quarterly. So if you want to stay up to date with DNA storage, reach out, become connected, and be part of our little ecosystem.
Fantastic. Dave?
What Esther said.
Yeah, it is perfectly wrapped. Well, both of you, thank you so much. It's and Dave, if people do want to reach you, what's the best way for they can find you? Of course, you're doing fantastic work with SNIA as well as at home office. But where do we best find a way to catch up electronically, if not IRL?
Well, people can. I mean, I don't know if. People can all reach me at dave.landsman@wdc.com if they welcome to take any questions or contacts. But yeah.
And of course, there's always great stuff going on with SNIA, and we just had SDC, and I know that we're looking at 2025 as for folks that are potentially looking to pick up membership. There's been a lot of neat changes. We just published a podcast with Dr. Jay Metz talking about new updates for the next year on membership. So folks that are keen on SNIA, or they do want to dig into more of what they can do with folks like the DNA Storage Alliance, definitely reach out to any of us here. Drop a comment, and again, it's an honor to share microphone time with both of you. I'm thankful for all I feel invigorated every time I read these papers, and this is awesome. So, and it's great to see that you're getting to do this and, create a future opportunity for so many folks. So thank you both.
Thank you, Eric.
Thanks, Eric.
Thank you for listening. For additional information on the material presented in this podcast, be sure and check out our educational library at snia.org/library.